So let's recall that we are trying to motivate the notion of limit, and for that we have already seen example 1, and in example 1 we have this, that is, there is the 150 feet cliff from the top of which a rock is released, and the rock comes down under the influence of gravity, under its own weight. So in example 1 we have already calculated two average speeds, namely the average speed of the rock during the first 2 seconds of its fall, that means during this time interval, and also the average speed of the rock in this time interval, which lies between the first second and the second second, and these two values we have already calculated. But now we are being asked to find the speed of the rock at t equal to 1 and t equal to 2 seconds at these two values, at these two instants of time, not over an interval of time. So clearly this speed is something other than the average speed. These are instantaneous speeds, that is, speeds at those instants of time. What does that even mean? That's what we have to understand here. Now, if one still thinks of this speed also as average speed by thinking of it again over a time interval, and that interval, for example, at this instant of time is, say, over this interval of time, which has length 0 because it's this singleton set 1. So shall we divide something by 0? That of course we cannot do. So this way we cannot calculate this speed, and we don't even really know what this speed means, but we can do something else, and that something else is that we can calculate again average speed, but not one average speed, but many average speeds over some intervals that are going to be made shorter and shorter in length, and then we will try to see what happens to those average speeds. Specifically, we are going to do this. Say we consider one time interval whose one boundary is this 1 second mark, and the other boundary is some 1 plus h seconds, where h is some positive real number. So then we will have a boundary, we will have an interval of time like this. In this interval we can calculate the average speed, and if we do so, the average speed of course will be this. Change in distance divided by change in time during that time interval. So the rock fell by this length or this distance, and that distance is 16 times 1 plus h whole square. This we have already seen in example 1, that when such a rock comes down under its own weight and nothing else, only gravity is acting on it, then the distance through which it falls is 16 times t square if the time that has elapsed is t from the point, from the moment of release. If t seconds have passed, then the rock falls by 16 t square feet. So this much the rock falls during this much time, and minus it falls during the first second of its journey by this much, divided by h, of course, the length of this interval. So this is one average speed, the average speed of the rock in this time interval. What we then do, we make h smaller, and hence we take the point 1 plus h closer to this 1 second mark. That is, we choose an even shorter interval, and then in that interval also we calculate the average speeds, and we continue doing this. So this way we calculate several average speeds. We get a sequence of average speeds. So you can imagine what we are trying to do. As we make the intervals smaller and smaller, it is as if we are trying to approximate this one instant of time, which is this 1 second mark, with those intervals. Of course, they are all having positive lengths, but we are making that length, which is h, smaller and smaller. That means we are taking h towards 0, or we are taking 1 plus h towards 1. So the intervals are as if the intervals themselves are being made smaller, shorter and shorter, so that they are tending towards a point, a single instant of time. Correspondingly, the average speeds also, maybe they are also approaching something, and intuitively we can say that that something should be the speed of the rock at the instant 1 second. Now if one actually does this, for here of course we are considering the 1 second mark, but in general if one does this for any time t naught, then the value towards which the average speeds will approach, that should naturally be in fact defined to be the speed of the rock at that instant of time t naught, and that's what we have done here. So here, because we want two such speeds, instantaneous speeds, speeds at some instants of time, once at t equal to 1 second mark and once at t equal to 2 second mark. So we have the table like this. So in this table, what the authors have done, or rather what we are doing, is that here t naught is 1, okay, and we are taking smaller and smaller h values starting from h equal to 1. So that means when our h is 1, actually the interval is this itself, the 1 second length interval, length 1 interval, having these two boundary points, one of which is this 1 second mark and the other one is 2 second mark. In this we have one average speed, and that average speed is 48. But then we choose a smaller value of h, 0.1. So instead of this interval, now we consider a much shorter interval. That boundary 1 second mark, that thing remains intact, but we change this one, the lower one. We raise it by choosing smaller and smaller h. So if we do that for this value of h, then in that smaller, over that smaller interval, this is the average speed. But then we choose a still smaller value of h, then 32.16. From 48 it came down to 33.6 in the second interval, then in the third interval 32.16, then 32.016, 32.0016. And you can of course see that there is a pattern, and you can guess that if one continues to do so, these values seem to approach the number 32. So according to our analysis and according to our intuition, common sense, we should say that 32 feet per second should be the speed of the rock at this instant of time. I'm saying we should say because we don't yet know what this speed should mean, but this is what it should mean. That is the most natural thing to do, and that's what we are going to do. So the instantaneous speed of the rock should be 32 feet per second at this 1 second mark. If one does the similar thing for this 2 second mark, then for those values of h, these are the average speeds. I mean, when h is 1, then we are considering the average speed over this interval, 2 second, 3 second, and then h equal to 0.1. So here we have 80 feet per second, 65.6 feet per second, 64.16, 64.016, 64.0016. So in this case, the instantaneous speed at the 2 second mark should be 64, or we will define it to be 64 feet per second. So that's what the solution to this example is. Now let's see what the authors have actually said. We can view at this whole thing like this also, that 32 is the thing that we want, which is a limiting value. We understand intuitively what that means in this example, although we have not rigorously defined what limiting value even means, but we understand that it should be 32 feet per second. So what is the relationship between this number 32 and those average speeds? Those average speeds are something we can calculate. For them we already have a formula, which is an algebraic formula, and it has a meaning. This 32, however, is something that we want. In this example this is 32, but in general still we don't know, because we do not have any definition for limit yet. But still we can look at this whole situation like this. Whatever this 32 ultimately turns out to be, I mean in our general definition, the average speeds are as if they are approximations to this instantaneous speed. As we take smaller and smaller intervals, the approximation gets better and better. It gets closer and closer to 32. That way also we can view at this whole thing. And the thing is that this approximation can be made as good as we want by choosing the interval sufficiently small. Okay, this sentence is very important. The average speeds are approximating that 32 value, but how good are these approximations? Of course, that will depend on some particular approximation value itself. If you take the difference of that approximate value and 32, you will get the error in your approximation. What I have said just now is this. So what I have said is that the approximation can be made as good as we want by choosing a sufficiently small interval. By that, what we precisely mean is this: the error can be made as small as we want by choosing a sufficiently small interval. If this is true, then we are ultimately going to say that 32 is the limit, or in this case the instantaneous speed of the rock at the 1 second mark. But let us now see what we have in the solution. In the solution, the authors write this, of course, whatever we discussed right now. So in the solution, we are now going to see that in writing. We can calculate the average speed of the rock during a time interval t0, t0 plus h, like that one that we wrote here. 1 comma 1 plus h, where h of course is some positive real number. Here in place of 1 we have general t naught, having length h as this. There we have 1, here we have t naught. And when in place of 1 you have 2, you just have to write 2 plus h, that's all. But this cannot be used to calculate the instantaneous speed. We cannot use this formula to calculate the instantaneous speed at t naught second, since we cannot divide by 0. Instantaneous within quotes, because we still do not have any formal definition for what instantaneous speed means. It will come. Because if you just simply want to use this to directly calculate or in fact define the instantaneous speed, you would have to substitute 0, h equal to 0. That is not allowed. But we can use it to calculate average speeds. But we can use it to calculate average speeds over shorter and shorter intervals of time. Okay, here it's written like this: over short intervals of time, increasingly short intervals of time. Same thing, over shorter and shorter intervals of time, starting at t naught equal to 1 and t naught equal to 2 seconds. And that's what we did in that table. If we do so, then we get a pattern shown in the above table, which right now is not available, but it's there in the text. from the table we find that the average speeds over intervals starting at t naught equal to 1 seem to be approaching the limiting value . And in fact, because we are talking about speed, so 32 feet per second, and that's why the speed of the rock at the time instant t equal to 1 second should be 32 feet per second. Yeah, that's what they have written. Oh, okay. Seem to be approaching the limiting value this as the why are the average speeds changing, that also we have to write as the length of the time interval decreases. So the speed of the rock at t naught equal to 1 second should be 32 feet per second. It should be. We are just simply saying that it should be, but we don't yet know whether it really should be this. This is only a suggestion that we have got from this small table. Similarly, the speed of the rock at t naught equal to 2 second mark should be, what is it, 48? No, 64, sorry, 64 feet per second. Keep in mind that these are only some ideas, and whatever I just said there after that explanation was over, I mean whatever I said was this, that the average speeds of the rock during those intervals whose lengths are getting shorter and shorter, these average speeds seem to be approaching 32. But how many such average speeds have we seen in the table? 1, 2, 3, 4, 5. Only 5. We cannot base our definition just on 5 values which seem to be pointing towards these numbers. But the actual definition of limit should have infinitely many values, because whatever I said there is this none. The average speeds are interpreted as approximate values, and this is the value that we want. The thing should be like this. The approximation can be made as good as we want by choosing a sufficiently small time interval. How good, that is our choice. And so we can make infinitely many choices. We can make, say, someone says something like this. Okay, I want the average speed to be such that the difference between the average speed and 32 is a very small number. How small? Say it is less than some 10 to the power minus 10, which is an extremely small number. Is that possible? Someone says yes, that is possible, because there exists such an interval which also has very small length, so that over this interval, if you calculate average speed, then that satisfies this inequality. Now these values are like challenges which someone gives us. Someone presents these as values as challenges, and we have to answer each of these challenges with one such interval. If we fail to answer even one challenge, then we cannot say that those values are approaching 32. So naturally, because there are infinitely many challenges in the form of positive real numbers, so infinitely many such approximate values or average speeds should be there involved in the definition of limit itself. The definition we will formulate, and this is the way we are ultimately going to formulate it. It's going to be a little complicated to understand the first few times, but once you get the idea, then it will become very natural, and then you will see that yes, this is how it should be formulated mathematically. Right now, from just this example, we cannot immediately see why we should go like this, but we are going to discuss some more examples also, and then only after some examples and much motivation, the authors are going to lay down this actual definition. Okay, we are somewhat still far away from this definition. Now let us also see one more thing. Recall that this is speed, but we are yet to see another type of rate of change, which is population growth. That will come in example 3, but before that, let us see something else. What is going on in this whole thing geometrically? If one draws a graph like this, the x-axis, on the x-axis we take time t, and on the y-axis we take distance y, or the vertical distance through which the rock is falling. Okay, now we already have a formula for y in terms of t, and this is just simply the formula, right? 16t square, and we already know how the graph of this equation should look. It will be a parabola. There is another side of to the parabola also, but in this case that other side does not have any physical significance, because our time really starts from 0. We do not have any reason to consider negative time. So when time is 0, y is also 0, because the instant the rock was released, it did not move at that instant, but then it started to fall. And as the time passes, it falls faster and faster. So that's why more and more it increases. Fine. So this is our 1 second mark, and this is our 2 second mark. Or okay, in order to make it even more clear and prominent, let me take these things a little apart. 1 and 2. So at 1 second mark, the rock has fallen this much, and at the 2 second mark it has fallen this much. Okay, so this is y1, which is let me give it some name. Say it is f of t. F of t is 16t square. So this is f of 1, and this is y2, f of 2. Okay, and now what we are doing, we are calculating average speeds. That instantaneous speed, whatever we are trying to guess here, that is something else. Okay, let's not think about that for the moment. We come back to average speed. Now what happens is this. What now I am going to do, I am going to join these 2 points by a straight line. And because we know the values, we also know the coordinates of these points. The coordinates of these points are 1, y1, and the coordinates of this point are 2, y2. Now we have already seen how to calculate the slope of a straight line passing through 2 points, a non-vertical straight line, and that slope for this line is y2 minus y1 divided by 2 minus 1. Let's keep 2 minus 1 as 2 minus 1 for the moment. But actually, what is this in this context of rock falling and everything? This is the distance traveled during the time interval 1, 2 divided by length of the time interval 1, 2. In other words, this quotient is the average speed of the rock in the second, and this in fact we calculated in example 1 also. So this average speed turns out to be numerically equal to the slope of this straight line, which is a secant line to this curve. Now if someone considers that process of taking smaller and smaller intervals, one of whose boundary is this fixed one, say one considers this point, some point, then the corresponding point on the graph is this. Now in this interval, in this slightly smaller interval, if one considers the average speed, then we get the slope of this other secant, which is a little like this. And if this process continues, then the secant will become like this. Okay, it will change. And don't you think that in the limiting case, the secant, when this other boundary tends to 1, that is the interval becomes vanishingly small, the secant will tend towards the tangent to the curve at this point. It's just a natural observation, and correspondingly the limit that we are talking about here, this 32, that is the value towards which those average speeds approach, that will become the slope of the tangent. It seems like this should be the case, and this actually is the case whenever such values exist. They do not always exist. I mean, any such process where you are making something smaller and the values, you are getting more and more values, it's not necessary that those values should always approach some number, and in such cases we say that limit does not exist. Other than those cases, in the other cases where limits do exist, there is this relationship between the slope of the tangent to the curve at that point and the rate of change. The rate of change in this case is speed, because we are considering time and distance. It may be something else also. For example, in example 3 we are going to see time and population. So that is rate of change of population. So we are going to discuss further, but in the next calculus video, about these things, and slowly we will approach towards the actual definition of limits, which you will see will involve these things: a challenge and an answer. Okay, so I just end things here itself. If you want to say something, you can write in the comment section below, or you can mail me. My address will be there in the description. And tomorrow we are going to solve group theory problems from Lee's algebra. So with that, I wrap things up. So see you tomorrow with Lee's algebra. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice day.